we first present algorithms that can personalize a speech enhancement system, that is, optimize them towards a single test-time speaker. For example, we envision a family-owned speech enhancement system should adapt very well towards the family members' voices and their home acoustics, but not for other situations. We're motivated to do this because it was previously shown that personalized systems can achieve a comparable enhancement quality using fewer parameters in comparison to more complex general-purpose speech enhancement models. However, fully supervised learning for speech enhancement inherently requires clean speech targets from the test time users, and that's often unavailable. So in this work, we present a self-supervised learning scheme to maximize the use of the abundant, noisy test time users' speech signals. Our proposed data purification method will examine the noisy utterances and find the parts of them that are clean enough to be used for training. So if we look at the top plot, for example, we can see that the areas where the green noise signal are louder have a lower instantaneous SNR, as shown with the red line in the middle figure. We train a speech quality predictor neural network, which shows reasonable performance in predicting the ground truth SNR values, shown in the purple line. The predictions, the purple line, are then converted to a score ranging from 0 to 1, where 1 means that the signal is clean in that part. Then we formulate a personalized speech enhancement problem into a self-supervised learning process, which is a pretext task that we refer to as pseudo-speech enhancement. This is shown on the bottom plot here. First, we inject further noise, which is this yellow source, onto the noisy test time utterances, as if they are the clean speech target. Hence, the enhancement network learns to recover the already noisy source S tilde, not S. This process is not good enough as it's quite far from reality. We improve the practicality of this process by introducing the purification concept. Instead of equally treating all the noise frames, we give a higher score to the cleaner frames so that they contribute more to the loss, and vice versa. Looking at our results, we can see these overall trends. Pseudo-speech enhancement, i.e. the naive self-supervised training without any filtration, relies too much on the noisy speech, which can actually hurt the enhancement model's performance. Our proposed data purification step, DP, greatly improves the training over the noisy speech data, which leads to a significant enhancement performance improvement. And we see that the smaller models gain greater gains. Therefore, personalization could be seen as a form of model compression. Thanks for listening.